Okay, this is sample problem 17.3. Select an appropriate weak acid from the table in the margin and describe how you would prepare a buffer with a pH of 9.50. Okay, so we're preparing a buffer. When we're preparing a buffer, what you want to do is you want to use the Henderson-Hasselbalch equation. So the pH is equal to the pKa plus the log of the conjugate, of the ratio of the concentration of the conjugate base. Oops. Let me make a little more space over here. There we go. Concentration of the conjugate base divided by the concentration of the weak acid. Okay? Now, notice that pKa is in that term, and notice I've selected the little table over to the right of different pKa's. So they're asking us, which buffer we're going to use, which weak acid and its conjugate base we're going to use to make the buffer. As a point of interest, what you want to do is you want to pick, if you can, pick an acid that comes closest to the pH that you're trying to make. One that has a pKa that's closest to the pH you're trying to get. So we're trying to get a pH of 9.50, right? So you want to pick an acid that has a pKa closest to that. It looks to me as though it's HCN, and that has a pKa of 9.31. The phenol, C6H5OH, is close. It's about 0.39 units off. But the HCN is only 0.19 units off, so that's a little bit closer. Now, HCN is poisonous, it's toxic. People really don't want to use it in the laboratory, so it's an interesting problem that they picked an acid that no one really wants to work with. It's a very dangerous acid. But in any case, we'll go with what they're asking. So we're going to pick the HCN because it has a pKa of 9.31. So what I'm going to do is I'm going to just go ahead and substitute in the numbers. The pH that we want is 9.50. The pKa of the acid that we're using is 9.31, okay? That would be that would be plus the log of the ratio of the concentration of the conjugate base. So that would be cyanide, just take the H plus off of the HCN, divided by HCN. Okay, so there you go. So now we've selected HCN. I guess I should write in here, we're going to select HCN. Again, because its pKa is closest to the desired pH, 9.50. Now what we're going to do is we're going to do a little bit of arithmetic. Generally, what you want to do is you want to isolate the ratio of cyanide, the conjugate base, to the weak acid. That's usually good enough just to answer that. Sometimes you can go a little bit further, but that's usually what we want to do. So let's go through the algebra of doing that. We're trying to get this term over here isolated by itself. So we're going to subtract the 9.31 from both sides. And that would give us the log of this ratio. Okay, well that's 0.19. Now do you remember how to get rid of the log? So if you want to get rid of the log on the right side, how do you get rid of it? It's the antilog, right? So you just take 0.19 and do the antilog. So we come over here, 0.19 antilog. Well, okay, 10 to the x is the antilog. So it's 1.55. In fact, I'm just going to round it to 1.5. That's usually good enough, but let me go ahead and explain a little bit further what this result means. What this means is that you've got to make a solution. Okay, so you have some large container. And the concentration of the cyanide has got to be 1.5 times greater than the concentration of HCN, right? 1.5 over 1 would be this ratio. So one thing that would work would be you could make HCN 1 molar and you could make CN minus 1.5 molar. Or just the ratio has to be 1.5. So it doesn't have to be 1.5 and 1. It could be 0.15 and 0.1, right? It's just the ratio has to be 0.15 over 0.1 is a ratio of 1.5. And then remember, for the conjugate base, you can't purchase cyanide. You have to get a salt. So you would purchase sodium cyanide or potassium cyanide. Those two salts would dissolve into water and give you CN minus. So we could use 0.15 molar KCN and 0.1 molar HCN, and that would give us a pH of 9.50. Okay? The actual concentrations you use depend on the situation. So I just made up a couple of numbers, 0.15 relative to 1, so that we get the right ratio. But you may, for some reasons, need to use larger or smaller concentrations. That's something that you would learn in a laboratory for the purposes that you're studying.